Let's suppose we have some sort of infinite series representation of a function. What do we need to be true in order to start integrate it term by term or differentiate it term by term and know that we're going to get something that matches the actual function we're interested in? What we didn't get into is how in the world do we come up with such a representation of a function? The last couple classes we just assumed that we had one. So that's what we're going to finish off today, is at least one approach to how do we get these representations in practice. And these are power series representations, which you'll see are Taylor series. You're going to see how do we get these, and where do they work, when do they converge? Of course, the other very common way of representing a function in terms of a series would be a Fourier series with sines and cosines. So here's a special case of what we've been doing. Special case of series of functions are things that have this form. Okay, so infinite polynomial. I know this question came up last class. Then for the n equals 0 case, the explanation would be that this is, there's something to the 0th power, that this is just 1 and that includes at x naught. So the 0th term is just a naught for any value of x. So there are some questions that we need to ask. For what values of x does this thing converge, first of all, and then secondly, when would we get uniform convergence? Is a little bit stronger because uniform convergence as well as us do integrals, take derivatives, do the kinds of things that we probably want to do as applied simplifications. Okay, so first of all, we need to ask what values of x lead to convergence. So for this, we're looking at an infinite series. We want to know when does an infinite series converge. This is, so for any fixed value of x, this is just standard convergence of an infinite series problem, and we can use whatever tests we know in order to work this out. So root test would be natural here because we have something to the nth power. Take an nth root of it. You could also use ratio test here to work this out. So let's just see what the root test tells us. The root test tells us what? That we need to look at the nth root of the objects that show up here, and then we want that to take the limit superior of that and have that be less than 1. The root test says, let's look at the lim sup of all of this. Okay, when we take the nth root of this, there's two terms here. There's the nth root of this. There's also the nth root of this, which suddenly doesn't depend on n anymore. So when I do this, I get something that doesn't depend on n times something that just depends on these coefficients. And we know that we need this to be less than 1 for convergence. So this motivates the definition of a radius of convergence. In other words, how big is this term, x minus x naught, allowed to be in order for us to still have a hope for convergence? So we'll define x minus x naught to be the number that makes this exactly equal to 1, and then we'll know that we need to be less than the radius of convergence to get convergence. So let's define a number r, such that r times the lim sup exactly equal to 1. This is going to be the radius of convergence. Okay, and now we're going to allow some different possibilities here. R could be 0 potentially. Okay, this could go to infinity. We'll allow for the case that R is equal to 0. R could be infinity potentially if this goes to 0. Okay, so there's some edge cases that we're going to allow here that are still going to give us the conditions that we need. Okay, and then we're going to find that the series converges if x minus x naught is less than R. Right, so if R is the number that would make this exactly 1, and as long as this is less than R, we're less than 1, we're in the situation where we have convergence of the series. So this is the first thing we need to know. When does the series converge at all? Right, so we're never going to try to plug in values of x that don't satisfy this condition, because we know we have to. This is the first thing we need, but then the second thing we need is not just, yes, the series converges, we need uniform convergence. We can't do the things we want to do without uniform convergence. So it's not a big jump to go from what we know about our radius of convergence to uniform convergence. So we had an easy test for uniform of convergence, this Weierstrass-M test, which we can get doing essentially the same calculation. So let's suppose that this series okay. I'll let x naught equal 0 here, just to keep notation simple, but of course this would all generalize just fine with other values of x naught. Suppose this converges with a radius of convergence R that is greater than 0. R equals 0 is not terribly interesting in terms of the series. R equals 0 means that the only value we can plug in here is x naught itself, which is boring. Okay, so suppose we have convergence with a radius of convergence R greater than 0. Now we're going to pick some real number k that is less than R. Okay, then we're going to find that convergence is uniform on interval from minus k to k. Okay, so we have a positive radius of convergence. It could be infinite also. Then on any closed bounded subset of minus R to R, we've got convergence. So if R happens to be infinity, we can say, well, we have uniform convergence on any possible closed bounded set. Then if R is finite, then we'll have to take things that are just a little bit away from R. Coming up to R where we may run into troubles. And the proofs, again, will follow from the Weierstrass-M test. And it's essentially exactly the calculation that we just did over there. We'll say that, well, the terms that we actually have, an x to the n, which depend on x. The Weierstrass m-test, remember, says we need to bound this by something that doesn't depend on x. And if the series of things that don't depend on x converges, then we get uniform convergence. So here we can bound this by an times k to the power of n. And now we're in business to do the root test on this series of constants. And as long as we pass just m-test helps. So if we do the root test, again, this is not actually different than what is already written on the board. The nth root of all of this. Well, k is strictly less than r. That's important. We think of k to be actually less than r. So this is going to be less than r times the lim sup of a to the n, 1 over n, and we chose r to make this 1. Okay, so root test said nth root of this, less than 1, strictly less than 1, which we've got. So this guy passes the root test. That means this guy passes the test for uniform convergence. So right away we can say, great, we have uniform convergence. And again, you could also do the ratio test in some cases, depending on what the structure of your AN looks like. Maybe the ratio test is easier, that's fine. You can use whatever tests are available to you to figure out where things converge, to figure out how to show convergence of this series that you're going to come up with for your Weierstrass m test. So that's good. Given an infinite series, a power series, we have a fairly easy way of checking, does this converge uniformly or does it not? So if we can come up with power series, probably we can use them pretty easily. So let's remember what the consequences of this were for us. One is uniform convergence means we can integrate. There's nothing else we have to do. We can integrate right away. Okay, so one result, which I don't even have to prove, I'm just, it's a straight consequence of this result and what we've just proved. So if the power series has a radius of convergence r, okay, and we decide, we pick an interval that we want to integrate over, and that interval is a closed bounded interval that keeps us less than a distance r away from our reference point, which is the origin here. Well, now we're in business, right? We're strictly within the radius of convergence. We know we have uniform convergence on this set, so we can integrate. Okay, so then right away we can say that the integral over a to b of the function that is equal to this series, the function that this series converges to. Integrating that function that this series converges to, is exactly the same as taking this series and just integrating it term by term. So we want to integrate it term by term. What do? An is a constant. We get x to the n plus 1 over n plus 1. And we plug in our limits. And we get a new infinite series, and the series is going to also converge to the same thing that we had originally, the value of this integral. So, I mean, this was our motivating example about a week ago. We had e to the x squared, and now we said if we can write down a series for e to the x squared, can we integrate term by term? This result says yes. If we can write down a convergent power series for e to the x squared, then we're in business. We can integrate it term by term. Maybe a little harder, a little more surprising, is we can also differentiate term by term. That's not quite an immediate consequence because there was a little more we had to show. We had to have uniform convergence, but then when we took the derivatives, we also had to get uniform convergence of the derivatives. And it turns out that we're extraordinarily lucky or something, and that's going to happen automatically with these power series. We don't have to do anything special. So this is, I will say, a non-obvious result, but it turns out that it follows pretty immediately from what we've already done. So that one I don't need to write a proof of, because the proof, it just follows immediately from what we've done, from what we know about integration of uniform and convergent series. This one needs a proof. So let's suppose that we have a power series. Okay. Our usual power series. And x to the n, suppose that this converges to a function f. And its radius of convergence r. Okay, then right away this is enough to tell us that the function it converges to is differentiable, and we can get at its derivative just by taking derivatives of this term by term. So straight away we have that f prime exists, and it's equal to, it exists and on, let's say on minus r. And it's equal to the result of taking this derivative term by term. Okay, I'm starting the series from 1 here, because up here, the first term recall was just a constant, so when we take its derivative, it goes away. So the derivative of the 0th order term is 0. So we're going to start here. And the radius of convergence is still r. This one again, not obvious, so we need to dig into this a little bit and figure out what's going on in here. Remember, we're already given, so we're given the power series convergence with this radius of convergence. That means we already know we get uniform convergence on compact subsets. Now we need to show that this guy also converges uniformly. That's what's needed to apply the theorem that we had last time, that the derivatives converge. Okay, so let's focus in on this guy, trying to figure out what's going on with this guy. So we need to look at the partial sum of it, I guess. So we have, on the one hand, partial sums of our original series. And the partial sums we can, of course, take derivatives of, because each partial sum is really just a polynomial. So these guys we can certainly take derivatives of. Okay, so what I want to do, I need to show uniform convergence. This guy is still going to be in the form of a power series. Okay, this is still in the form of a power series, so everything we've already talked about today, it holds for this guy. So we really just have to do the usual test for a power series and to find out its radius of convergence. And what we're going to find is that we can relate it back to the radius of convergence for this original. All right, again, there's no magic tricks we have to do here. This is still a power series. Okay, so this is still a power series. So let's let R not be the radius of convergence for the original. And let's let R1 be the radius of convergence for our derivative. Okay, so for R naught, I'm just going to write down what it was. It came from doing a root test. So we do the root test on these things. We knew that 1 over R naught was equal to the lim sup of an to the 1 over n. I'm going to do the same root test on this guy. Now instead of an here, I'm going to have an n here. That's the only difference. So my radius of convergence for this guy is going to be n to the 1 over n. And what we want to show is actually these are the same values. So what's new here? This is, let's just break it up. N to the 1 over n times an to the 1 over n. Now we know what this term is trying to do as n gets large. This term is trying to go to 1 over r naught. So what we need to assess is what does this term do as n gets large. Well, this is just a straight ordinary limit problem at this point. This limit exists. Do you know what this limit is equal to? Yeah.
Isn't it 1?
This limit is equal to 1, exactly. All right, and how would you do this? This might be a good place to try to bring in L'Hopital's rule or something. So let me not do the calculation, but you can certainly check the calculation. We have the tools for that. This limit is equal to 1. So if I want to know what is this whole thing doing as n goes to infinity, well, this quantity is approaching 1. This quantity, at least the lim sup of this quantity, is approaching 1 over r naught. So taken all together, 1 over r1 is going to be 1 times 1 over r naught. Which means indeed the radius of convergence is identical. Okay, so we found the radius of convergence of this, right? That means on any closed bounded subset, we're going to have uniform convergence of the derivatives itself, and that means we're in business. So let's let x be any number that belongs to minus r to r. Okay, let's choose some value k that is between x and r. Right, we can always do that. X is less than r, so we can always find something in between these two things. All right, that means that indeed this series let's call it this. The partial sums Fn prime converge uniformly on the closed bounded subset right? As long as we're within the radius of convergence, as long as we pick something that is within minus r to r, we know, we just showed that the Weierstrass-M test tells us convergence is uniform. So these partial sums converge uniformly, and that was the extra ingredient that we needed last class in order to say yes, we're allowed to take derivatives. So without even knowing what they converge to, we can just say actually they converge to what we want. We proved that last class. Okay, so from last class, Fn prime converge exactly to the thing that we want. Right, so now we're in business. You give me a power series. I have an easy way of figuring out the radius of convergence. Right? Root test, ratio test, they're easy tests to apply. And then we're in business. Then we know without doing any more work, we can start taking derivatives, we can start doing integrals. All of these tools are now available to us. Right? So for example, I think this is one that we broke down last time. And we worked out itself because this was a geometric series. Okay, so for geometric series, we had exact formulas for the sequence of partial sums, and then we could take the limit. So we worked this out last time. But now we can start taking derivatives of this term by term equation. Okay, so since we know this converges, for x less than 1, our radius of convergence is 1 here. Then, without any more work, I can say, great, let's take derivatives of both sides. Okay, and I can be confident that these series will agree with each other. Okay, so I have a minus 1 to the n, bring down the n, and then an x to the n minus 1. And right in that way, we know this converges, and we know what its radius of convergence is. And we know that the series converges exactly to this, without doing any additional work. Okay? And we know this is true now for x less than 1, and there's nothing else we have to do to prove that. In fact, we could take as many derivatives as we want. Now I have a convergence series here. I know its radius of convergence. I can take more derivatives. So I can start computing higher order derivatives of my original, and I can keep going as far as I want to. This keeps working once we have these convergent power series. So let's suppose we know this. F of x is a power series. We can keep taking derivatives. Okay, so suppose this is true for x less than r. Then, all right, this is true for x less than r. But if this is a conversion power series, once again, I'm allowed to take its derivative. So I can certainly bring down another derivative. And I can keep going as long as I want. I can keep taking as many derivatives. Every time I take another derivative, I arrive at another convergent power series with the same radius of convergence, which means I take another derivative. And in general, if I go to the case derivative, I would see what happens. You start to see the pattern here. Every time I take another derivative, I have another term that just becomes 0, so my index starts a term later. We're going to start from k to infinity. And we keep bringing down another power. So we're going to have n, n-1, n-2, and so on. Which is the first few terms in n factorial, and the way we can write that in a simple way is to say, well, let's have n factorial, and then divide out the terms that shouldn't really be there. So in this case, which terms shouldn't really be here? Everything from n-2 and beyond shouldn't be. Here, if I had an n factorial, everything from n-1 and beyond shouldn't be. In general, everything from n-k and beyond shouldn't be there. An stays put, and x to the n-k is here. And this still converges to the radius of convergence. And now we can start asking ourselves, well, what are each of these ANs? We've played this game before with finite series, what is maybe a good choice of the ANs. But we could play this game again and say, somehow, here x not equals 0 is my reference point. So what happens when I plug in 0? Well, when I plug in 0, most of these terms vanish. Just the first term, the case term here, gives me my constant term. So in general, when I plug in 0, almost all of these terms vanish, except for the n equals k term. We get k factorial over 0 factorial, ak. That's my constant term. Everything else, when I plug in x equals 0 is 0. So playing this game, being allowed to just keep taking derivatives over and over and over again, lets me say something about these coefficients. This coefficient, if I can write down a convergent power series, coefficient has to have this form. There's no other way of writing down a convergent power series. Right? And that's a reasonable question one might ask. Is the power series representation unique, or are there different ways of writing down infinite polynomials that give the same function? This is unique. There's only one way of picking these ANs that will actually have the potential of giving me the function that I want. And this should look familiar. We've seen terms that look like this before when we did finite series. We did Taylor series with finite number terms, and all of the coefficients look exactly like this. But we had to stop at some point. Now we know if we want to go to infinity, if we want to take an actual infinite series, if we have a power series that converges to our function, then it is the Taylor series. So, if a power series converges to f, then it must be the Taylor series. strategy. Say I have a function, I'd like to come up with a power series representation of it. Well, if I'm going to be successful, I have to use these coefficients, the coefficients that come up in my usual Taylor series. There's not going to be any other way of coming up with a power series representation. There's a follow-up question that we should be asking. We said, if I happen to have a power series that converges to F, then it's the Taylor series, and then I'm in business. I can do whatever I want. But that's not quite the same as saying that the Taylor series of a function always converges to that function. That's a different question. And it turns out the answer to that is not quite the same. So our follow-up question should be, suppose F is infinitely differentiable. Let's suppose also that the Taylor series let's call it T of X. Has a radius of convergence R. Okay, so we have a function f that has all the derivatives, right? We see from this calculation that if we're going to be able to write down a power series, it must be the case that all the derivatives of f exist. It has to be infinitely differentiable. We won't be able to do this otherwise. Okay, so suppose I have a function that's infinitely differentiable. I go ahead and I write down the Taylor series. Okay, so I write down the Taylor series using exactly these as my coefficients. And I look at the Taylor series and I see, great, it's convergent. It has some nice radius of convergence, positive radius of convergence. And my question is, does it converge to the thing that I want? Right, so here we said if it converges to the thing we want, it's the Taylor series. Now we're asking the full question, if it's the Taylor series and it converges, does it converge to the thing that I want? And these questions, it turns out, don't have the same answer. So let's take a little example. Let me define the function e to the minus 1 over x squared. And I'll plug the hole in a way that makes this continuous. Right? So as x goes to 0, this exponent here goes to minus infinity, so the whole thing goes to 0. Okay, so we have some function that, let's see, what does it be? It's 0 here. As x goes off to infinity, we're having something that approaches e to the 0, which is 1. It's going to do something like this. If I want to start taking derivatives of this function, I'll do the first derivative, but then you could use, say, induction to prove what all the higher order derivatives are. Okay, so let's do f prime of x. Well, if x is not 0, we just take the derivative the way we normally would. If f is 0, since I have this piecemeal definition, I'm going to use the usual definition of the derivative. And give my plug once again going into the final. If you have to work out a derivative, or if something is differentiable and you can't use a formula, this is what you come back to, the definition. There's a particular limit you have to check. So we need to check the limit as x goes to 0 of f of x minus f of 0 divided by x minus 0. The details of this, you'll find that this limit is 0. And the numerator and the denominator are both going to 0. We tried L'Hopital tool, but the exponential dominates things. Exponentials go to 0 faster than linear functions go to 0. Okay, so in general, we're going to have f prime of x is equal to, all right, so take the minus 1 over x squared, the derivative of that, and we're going to get a 2 over x cubed, I guess. Okay, and 0, and x equals 0. All right, once again, this is continuous. So this guy goes to 0, and the exponential is going to go to 0 a lot faster than the polynomial in the denominator does. So this is still continuous, and it's still differentiable, and you can keep taking derivatives. So it's an exercise, you can try on your own if you want to, I'm not going to do it here. You can keep taking higher derivatives of this. And what you'll find is that at the origin, you keep getting derivatives of 0. So this thing has 0 curvature at the 0 derivative at the origin, it has 0 curvature at the origin actually, and then the curvature becomes positive as you move away from the origin. In fact, it has 0 third derivative, 0 fourth derivative. These derivatives are all 0. So we'll find that f double prime equals 0 at the origin. Triple prime equals 0. In fact, all of these derivatives equal 0 at the origin. Okay, so once we know all the derivatives of a function at the origin, we can write down its Taylor series. So the Taylor series is, okay, we have 1 over n factorial, the nth derivative at the origin, times x to the n. And all of these terms are always 0. Okay, so we wrote down the Taylor series. The Taylor series has an infinite radius of convergence, right? The Taylor series is just identically 0. So the radius of convergence is actually infinity. But this Taylor series is not converging to the function we wanted. The only place where they agree is right at the origin, at this one point. Okay, so despite the fact that we wrote down a Taylor series, we worked out its radius of convergence, which was the best we could hope for, it's infinity, but that doesn't mean the Taylor series is converging to our original function. So this is a little warning. Remember, when we wrote down Taylor remainder theorem, the Taylor remainder theorem did not say anything about infinite series. It said we can write down a finite series, and then we have a bound for what our error is. It didn't say we could take that to infinity. It didn't say that the bound on our error was small. It just said this is what the error is. And it might be small, it might be large, we don't know. So this is the warning about Taylor series that I'm coming back to. It's very important when we write down our theorem. We know that that's for the finite series. And you want to be more careful if you want to take this to infinity. So in this case, Taylor series converges, but T of x converges, but clearly not to our original. Except at the origin, which is boring if you've only got 1 point. So what's going wrong here? If we want to know what's going wrong, we should come back and ask ourselves, what does Taylor remainder theorem tell us? Taylor remainder theorem says, well, it tells us that f of x was equal to the n order Taylor approximation plus an error term. Now we're in a situation where actually these, we can think of these nth order Taylor approximation as an nth order partial sum. These are a sequence of partial sums. So suppose that we're in a happy situation where the sequence of partial sums does indeed converge. We have a convergent Taylor series. That doesn't automatically guarantee us that T of x is equal to f of x. That's only going to be the case if this remainder term also goes to 0 as we let n go to infinity. So if we want to know, can I use a Taylor series, an infinite Taylor series, and have it be equal to my function, we need to know what happens to this remainder as n goes to infinity. F of x will equal T of x if this remainder term goes to 0. Okay, so what was the remainder term? Let's remember. The remainder term looks kind of like the next term in the Taylor series. So it had a 1 over n plus 1 factorial, which as n goes to infinity, this certainly goes to 0. But then it had this derivative evaluated somewhere, we're not sure where. And then it had this term of the form x to the n plus 1. Okay, so what's happening here? As n gets large, okay, indeed as n gets large, this goes to 0, it goes to 0 quite quickly. But it's not necessarily the case that these other terms go to 0, right? This term will go to 0 or to infinity depending on how big our radius of convergence is. At least if we stay within x less than 1 in magnitude, this will go to 0. But what about this guy? We're not guaranteed that this goes to 0. We're not guaranteed that it even stays bounded. It could be the case, and we can expect this maybe with simple functions. Every time, say I just have a polynomial. Every time I take a derivative, I bring down another n. I bring down another factor. Things get larger. Now, if I have my derivatives getting larger too quickly, the blow up in here might just overwhelm the attempts to go to 0 from here. So there's more than just, yes, all the derivatives exist. We need all the derivatives to exist, but also not to grow too quickly as we take larger derivatives. Because again, we're not, in this example, at 0, these derivatives were 0, but as soon as we go away from 0, they might become quite large quite quickly. And the error term says we're not just plugging this in at 0, we're plugging it in at some point nearby, and the derivatives may be large. So this is the real danger here. higher derivatives, although they exist, may get large too quickly. I mean, this is an issue that comes up if you've taken any numerics classes and looked at interpolation or trying to fit a curve to some data. You have some scattered data points and maybe you want to fit a polynomial through it. You might think, well, the more data the better, we can fit better, but what you can actually find in practice is that the more data you have, the more wildly things oscillate and you get worse and worse approximations to what you actually want. It's a similar issue that's at play there, is that you have these higher derivatives showing up in your error term and they may not be well behaved. So more is not always better. So we need this to be able to stay under control for our Taylor series to work. And this gives us a condition when we know our Taylor series actually works. Okay, so let's suppose that f is infinitely differentiable. On some interval, let's say from minus r to r. And moreover, let's take a look at what's going on here. The limit, as n goes to infinity of all of this, is equal to 0. Okay, and this should be the case for every value of x, right? Because we never know what we're plugging in here. It's not the same as x. So we put in our worst case for x here, which is r. Then we say, well, let's check all the possibilities here. So if this is true for every x in our interval, if this condition holds, now suddenly we're in business. Now if this condition holds, suddenly this remainder term is going to go to 0 as we take more and more terms, which means indeed our Taylor series will recover our actual function. So if all of this holds, then the Taylor series will converge uniformly to the thing that we actually want. Okay, so let's take one or two examples of using this. Let's start with the previous function, which we looked at a little bit last class. We looked at its Taylor series, and we saw that actually its Taylor series gives us the right thing. But we did it using kind of an ad hoc method where we happened to get lucky that the derivative equaled the thing, and we solved the differential equation. Let's use a more systematic approach here and see what happens actually to the error term, the remainder term in our Taylor series. Okay, so what happens in our Taylor remainder term? In this case, Rn plus 1, Rn has this form. The n plus first derivative, the derivatives of e to the x are always e to the x. So that's going to be e to the c somewhere. Times r to the n plus 1 divided by n plus 1 factorial. So let me start by having this as x to the n plus 1. And then we say, well, what's the worst case this could be? The worst this could be is if we come up right to the boundary of our domain. And we have e to the r, n plus 1 divided by n plus 1 factorial. And we want to know what happens to this as n goes to infinity. There's a couple different cases. So let's say r is some fixed number. This is the main we pick. So e to the r is just a number. We don't have to worry about that. If r happens to be less than or equal to 1, then this whole thing is going to stay less than or equal to 1. So we'll have some number, something bounded, divided by something that goes to infinity, and it automatically goes to 0 and we're in business. So if r is less than or equal to 1, then without much work at all, we get that this is bounded by something that goes to 0, and the Taylor series certainly works. So this means that the Taylor series does what we want. If r is bigger than 1, it's not quite so obvious what's going to happen here. So we need to do a little bit more work to figure out what happens when r is bigger than 1. So r is some fixed number. R is the number that we picked to be our domain space. We care what happens when n is large. So we care about n large. And certainly, n will eventually get much larger than r. So eventually, n is much bigger than r. Okay, so I'm going to kind of pick an integer where roughly this transition happens, where they become approximately equal. So let's just choose some m, some fixed m. Okay, so such that, let's say m over 2 is bigger than r. Okay, eventually this will happen. Eventually we find an integer that's bigger than 2r, and then we're happy. And now we're going to say what happens as n gets large. So for very large n, we want to look at this object. E to the r, again, e to the r is just a number, it doesn't matter, but we want to look at the rest of this object and see what happens to it. So r to the n plus 1 divided by n plus 1 factorial. Both the numerator and the denominator involve multiplying a bunch of things together. In fact, both of them involve n plus 1 multiplication. This is r times r times r times r a whole bunch of times. This is n plus 1 times n minus 1 a whole bunch of times. So I can certainly break things up this way. Eventually we get to this integer m that we picked. And eventually we keep going and we get to n. And there's an exact match in the number of terms. Right? There will be exactly one r for every one of these terms in the denominator. Okay, so this down here, this is some fixed quantity. It just is what it is. M is a fixed number, R is a fixed number, so that's just some fixed quantity. What's going to be interesting over here is that we're going to see that, well, if R is less than M over 2, R is less than the denominator over 2 for all of these terms. So we know that Okay, so I'm going to use that figure. I'm going to look at this and say, well, this r is less than n plus 1 over 2. This r is less than n over 2. This r is less than n minus 1 over 2. And I'm going to keep going until I get to this point as my cutoff for where I'm able to do that. Okay, so I'm going to say this first r was less than n plus 1 over 2. This next one was less than n over 2. And so on. Eventually I have n plus 1 over 2. Eventually I have n over 2. And then I have whatever is left. Whatever is left is the remaining, so from here to here, I can use that trick. Now what's left? I have m minus 1 more powers of r divided by m minus 1 factorial. And then you look through here and you say, well, this actually simplifies to a half. This simplifies to a half. This simplifies to a half. All of these terms simplify to 1/2. We're going to have 1/2 times 1/2 times 1/2 times this leftover bit. How many of these are there? Well, there's n plus 1 minus the m minus 1 terms that didn't get included in this. And this guy is just a number. It doesn't depend on n, it's just a number that depends on r. So we can simplify this quite a bit. This is n minus m plus 2 times this number that doesn't depend on n. Now, so this is what happens for n large. We're interested in n being very large. We're interested in taking n out to infinity. Okay, so as I take n to infinity, again, m is a fixed number, 2 is a fixed number, this is all a fixed number. What happens to 1/2 as it raise it to a power that's very large, going to infinity? It just vanishes, it goes to 0. So as we take the limit as n goes to infinity of r to the n plus 1 over n plus 1 factorial, that's going to be bounded by, let me pull this term out in front. One half to this very large power, which goes to 0. Okay, so what was the thing that we needed in our remainder term? We said that our remainder term as we take n to infinity was bounded by e to the r n plus 1 divided by n plus 1 factorial. I should have a limit in front of this. E to the r n plus 1 over n plus 1 factorial, and this we now know goes to 0. So indeed, as n goes to infinity, our remainder term vanishes. And that's what we need to justify taking the Taylor series, the full infinite Taylor series. So right away we can say, great, indeed, e to the x is equal to its Taylor series. case, there was nothing particularly special about the R that we picked. Could have been anything. So this actually works for any R. And indeed, this works. That means this works for any value of x. This Taylor series representation is valid for all x that are real numbers. Okay, so it's a bit of work doing the calculation. The good news is that kind of calculation, that kind of term, shows up in a bunch of other different Taylor series, so you could, next time you see something that looks like this, you can just say, oh, I know what that does at 0. Any questions on this, on Taylor series conversions? Right, so we know if we have a Taylor series representation that converges to the function we want, we can do integrals, we can take derivatives, no problem. And now we know how to figure out if that's the case. This is remainder term that we have to look at. So let me take one more example that is going to be rather less work. Let's take the sine function. Okay, so you could write down a Taylor series of this, that you know what to do. Now we're interested in what happens as we let n go to infinity. So we're interested in what the remainder term is going to be. So this, like always, is fn plus 1 somewhere over n plus 1 factorial times x to the n plus 1. Now, we never know what value of c we're planning to plug in here, but we know something about what happens when we take derivatives and higher derivatives of the sine function, right? It bounces between sine and cosine functions, and those are always bounded by 1. So we're certainly not going to be in the situation where this derivative starts blowing up badly on us and destroying things. So right away we can say, well, this is less than 1 over n plus 1 factorial. X is less than or equal to r. Okay, and here, once again, we're in business. This is the same term that we just worked out. So we just showed that this goes to 0. We just showed that this goes to 0. For large n. So we can Taylor expand the sine function or the cosine function, or in general anything where the higher derivatives stay bounded on us, right? If the higher derivatives are always bounded by some fixed number, then we're in business. We can Taylor expand. So we've got a big class of functions where this just works. If it doesn't just work, then okay, we have to go back to this and say, let's try to figure out when this goes to 0. Taylor series for the sine function and for many others. Converges. And it converges to the thing we want. And once again, it really doesn't matter what value of r we put here. We can put any value of r here we want, and the argument goes through. So this converges globally for all possible n's. Okay, so this is sort of the conclusion, the climax of what we've been trying to do for the last week and a half. To say, can we use this idea of infinite series to give us representations of functions that actually do what we want? Now we have a clear way of doing that. Again, you can go try to play these games with Fourier series as well, because those are also very, very useful in math. But that's where I'm going to leave us for the contact for this class.